The second topic is the array factor in array antenna. First, let me explain the word factor. In an expression such as A, B, C, each quantity in the product is called a factor. In this case, A, B, and C are factors. In contrast, in an expression such as A plus B plus C, A, B, and C are called terms. So the word factor is used for multiplication. Now let us move on to array antennas. An array antenna is formed by arranging several antennas together and making them work as one antenna. Each individual antenna in the array is called an element. So, for example, if an array has 5 antennas, we may call it a 5-element array. The advantage of array antennas is that by arranging the elements appropriately, we can control the directivity. Then, what is the array factor? The directivity of an array antenna is given by the directivity of a single element, multiplied by the array factor. That is why it is called a factor. So the main question in this topic is the following: how can we construct an array factor with the directivity that we want? Now, I would like to explain the mechanism of an array antenna by using plotting software. We will use a free plotting software package called GNUplot. I think many of you may already know it. Now let us make several settings for the animation. First, since we will handle complex numbers, we define the imaginary unit. This is written as 0.0 plus 1.0 times j. So in other words, we are defining j. Let us set the angular frequency to 1.0. This is the angular frequency. Then the ordinary frequency f is the angular frequency divided by 2 pi. The period is 1 over f. Also, let us set the speed to 1.0. This does not necessarily mean meters or seconds. Please regard it as some normalized value. The wave number can be defined by c divided by omega. The wavelength may be written as 2 pi divided by k, or it may also be defined from the speed and the frequency. Now let us define the distance between r and r0. That is, we define the distance between x0, 0 and xy. Here, x0 is the position of the antenna, and we will place antennas at various positions. The point xy is the position where we observe the radiated electromagnetic wave. Then we define, as a function f, the actual strength of the electromagnetic wave that appears there. X and y represent position. Suppose we want to obtain the electromagnetic field strength at that point. We also use the time t. In the excitation, we will shift the phase, so let us denote that phase by a. And then we specify the antenna position x0. It is a little complicated, but the settings are like this. What we want to do is the following. This is the distance between the positions of the vectors r and r0. Since we will display an animation, let us use 10 samples per period. To draw a color map, we make these settings. Also, in order to match the aspect ratio, we set it like this, and we set the number of sample points to 50 by 50. Let us try these settings. The time is I times the period divided by the sampling number. The x range is from -20 to 20, and the y range is also from -20 to 20. For example, we plot this quantity. Then we pause for 0.03 seconds to watch the animation. The result looks like this. Let me show it once again. It looks like this. Nothing special is happening. It is simply a situation in which a periodic electromagnetic wave is emitted from here. Actually, the amplitude should decay, but here we are looking at it without taking that decay into account. For example, if we shift it sideways by 1/2 wavelength, nothing particularly strange happens. The center simply moves to this point. Or if we shift it by -1/2 wavelength, it appears shifted like this toward the left. Now let us see what happens if we add all of them together at once. We can add them by using sum. I runs from -1 to 1, so we add the 3 cases I equals -1, 0, and 1. What we add is I times lambda over 2. When I is -1, it is shifted by minus lambda over 2. When I is 0, it is not shifted, and when I is 1, it is shifted by lambda over 2. If we plot this, it looks like this. It now looks quite different from the previous one. It is a little hard to see, so let us change the color range to -2 through 2. If we look again, it takes this form. In these directions, a strong electromagnetic wave is radiated, whereas in this direction, a strong wave is not radiated. Furthermore, I think you can see that in this direction, almost no electromagnetic wave is radiated at all. Why does this happen? The reason is that there are 3 antennas here, and in this direction the phases of the waves emitted by them match one another exactly. They interfere constructively, so the radiation becomes strong. For example, in a direction where almost nothing is radiated, the waves emitted from this antenna and this antenna cancel one another exactly, which means that this direction corresponds to such an angle. In this way, by arranging multiple antennas, an array can control the directions in which the waves reinforce or cancel one another. Now let us shift the phase of each antenna. For example, let us shift them by pi/6. If we do this, the direction in which the wave is radiated changes slightly. And let us make it pi/2, for example. Then the radiation becomes strong in this direction. In this way, if we shift the phase of each antenna, the places where the emitted electromagnetic waves come into phase also change. If the place where the phases match changes, then the strongest radiation direction also changes. This is the mechanism of an array antenna.